Hello everyone, welcome back to the channel Upgraded than yesterday. Let's continue with the second part of the video where we are learning about how to make a class thread safe. If you have not watched the first part of this video, please watch that before watching this video to get more clarity on the topic. Let's start with the second part of the video. Thread safety by using synchronized keyword. Synchronized keyword is the most traditional way to ensure thread safety. It ensures that at a time, only one thread can execute a block of code using an intrinsic lock. Suppose there are two threads, thread A and thread B, and during the execution, suppose the thread B got intrinsic lock and execute the synchronized block. Then thread A will have to wait until thread B releases the lock. There are two ways to use synchronized keyword. Synchronized methods. Here the synchronized keyword is used in the method declaration. It locks the entire object disk. That means all the synchronized methods will be available only to the threads who is holding the intrinsic lock. Although all other non-synchronized methods will be available for all the threads to access. Synchronized block. A synchronized block is a block of code wrapped in a synchronized statement that locks only a specific section of a method. It locks the entire object. That means it also uses intrinsic lock, same as the synchronized method, but it reduces the scope of the lock. The main limitation of synchronized mechanism is if a thread is waiting for a lock and the other thread is not releasing the lock, then the waiting thread has to wait for forever. This is called starvation. Thread safety by using volatile keyword. Look at the class counter. The volatile keyword always applied to a variable while defining a variable in Java. Volatile keyword tells the JVM that never cache this value. Instead of caching, always read and write the value to or from the main memory. A volatile variable guarantees that the latest changes made to the variable will be visible to every thread, but it is not guaranteed that the atomicity of the variable. Visibility guaranteed. Look at the code. Suppose the current value of the count is 10 and the thread executes the increment method. So the value become incremented and it become 11. Now thread B executes print method. It will see the updated value, which is count is 11, and will print the value. Atomicity is not guaranteed. Look at the code. Look at the count plus plus. Actually it takes 3 steps to complete the operation. Read the value from the main memory, then increment by 1, then write the value back to the main memory. Now suppose thread A reads the value as 10 from the main memory and then incremented the value as 10 plus 1 is equal to 11 and then writes back to the main memory. But before thread A writes back to the main memory, thread B reads the value and which is still 10. Now thread B does the same operation to increment and it becomes 11 and writes back to the main memory. But ideally the value of the count should be 12. This is where atomicity is failed. To overcome this issue, Java has introduced atomic classes that we are going to understand next. Thread safety by using atomic classes. Atomic classes are part of java.util.concurrent.atomic package and was introduced in Java 5 release. Atomic classes provide thread safety by using cache, that is compare and swap mechanism. Compare and swap mechanism is nothing but a CPU instruction that does 3 things. First, read the current value. Second, compare the current value with the expected value. Third, if both the current value and expected value is same, then write the new value to the main memory. If they don't match, then retry. All these 3 steps happen as a one uninterruptible CPU instruction. Here no locks, no blocking, just a single hardware instruction that cannot be interrupted. This is how it guarantees both visibility and atomicity. Look at the class counter. Here atomic integer and atomic class is used to handle the counter. Let's understand with thread A and thread B how it guarantees visibility and atomicity. Suppose both thread A and thread B wants to increment the count value at the same time. Let's consider current value of the count is 10 in main memory. Now let's explain thread A execution. Step 1. Read the value from main memory, which is 10, so the expected value will be 10. Step 2. Compute the new value by doing increment operation, so the new value will become 11. Step 3. Apply cache mechanism. Here current value is 10, expected value is 10 and the new value is 11. Since both current value and expected value is same, so write the new value 11 to the main memory. Thread B execution. It is getting executed at the same time. So step 1. Read the value from main memory, which is 10. So expected value is 10. Step 2. Compute the new value by doing increment operation. So the new value will become 11. Step 3. Apply cache mechanism. Here current value is 11 as it is updated by thread A. The expected value is 10 and the new value is 11. Since current value is not equal to expected value, so thread B will retry again. Thread B, retry, refresh rate. Step 1. Read the value from main memory. This time it will be 11, so the expected value will be 11. Step 2. Compute the new value by doing increment operation. So the new value will become 12. Step 3. Apply cache mechanism. Here current value is 11, expected value is 11, so new value will be 12. Since current value is equal to expected value, so write the new value 12 to the main memory. We could see retry logic has solved both visibility and atomicity issues. Although atomic variables are simple, lock-free and faster, but there are disadvantages of atomic variables. For example, it only works on single variable. It cannot coordinate multiple variables atomically. The compare and swipe mechanism retry loop increases overhead of CPU instruction, which may impact on the performance.